All right, today is day one of section 6.3. There are two types of probabilities in section 6.3. We're going to be doing binomial first. Before we can actually dive into the binomial probability stuff, there's some background stuff that the book assumes you know that we need to address before we can specifically get to binomial probability. Okay, first thing we're going to talk about as a prerequisite skill is the idea of a permutation. So these are some permutation examples. How many different ways can the following symbols be arranged? Well, if you're arranging these symbols, it means you have to make 5 choices. How many different ways can you pick which one comes first, which one comes second, which one comes third, which one comes fourth, which one goes last? If there are 5 symbols, there are 5 ways to pick the first one. After you choose the first one, it can't be the second one as well. So it goes down by 1, down by 1, down by 1, down by 1. Okay, this happens often enough in probability and statistics. That gets its own symbol. Okay, this does not mean 5 with great emotion. 5 factorial, the factorial symbol is the exclamation point, means you start at that number times 1 less, times 1 less, times 1 less, all the way down until you hit 1. How many ways could a president, vice president, treasurer, and secretary be elected from a club of 20 members? So if there's 20 people, there's 20 ways to pick who's the president, 19 ways to pick who's vice president, 18 for treasurer, 17 for secretary, and then multiply it out. Okay, there are 16 contestants competing in a beauty pageant. How many ways can the judges award first, second, and third place prizes? Well, 16 ways to pick the winner, 15 ways to pick who comes second, 14 ways to pick who comes third. All right, permutation is an arrangement of R objects selected from n possible objects. The order of arrangement is important in permutations. So in this formula we're going to talk about here, n represents how many people or how many things or how many items we're selecting from. So in this case, the n would be 1, 2, 3, 4, 5. In this case, the n would be 20. In this case, the n would be 16. The R is how many of them are we picking? Well, here we're picking all 5. Here we're choosing 4. Here we're choosing 3. The key thing about a permutation that's important to what we're ultimately getting at here is the order in which you're chosen matters. Which one is first is different than which one is second when the whole point of the question is how many different ways can it be arranged. Being president is being different than vice president. Winning the beauty pageant and coming in second are 2 different things. The order in which you're chosen matters. Okay, the number of permutations can typically be found by using the fundamental counting principle as we did in the previous 3 problems. They can also be found by using this formula right here. So we're going to be having NCR, combinations, we're going to get to in a moment. And this is NPR, which stands for permutation. So n factorial, that's how many things we're picking from. R, how many things we're actually picking from that larger group. And then we plug it into that formula right there. All right, now in contrast to a permutation, zoom in on that a little bit, we have combinations. A combination is a set of items chosen from a larger set without regard to order. The formula to find the number of combinations of n objects taken R at a time is. So instead of NCR, we have NPR. There's also a different notation for combinations where you have one number on top of another one inside of parentheses. This is assumed to be a combination. This is actually the way it appears on the formula sheet for the AP statistics exam. This is a little bit more convenient because it matches the calculator keystrokes, which we'll get to in a moment. But you have to be comfortable with both. It's a very similar formula. Referring back to the previous slide here, the n factorial on top, n factorial on top, n minus factorial on the bottom, n minus factorial on the bottom. This has an extra r factorial on the bottom. And that's the mathematical way of accounting for the fact that order doesn't matter. Now, with these permutation problems we just finished, you don't have to use this formula. Regular fundamental counting principle from like 7th grade works just fine. Combinations, typically the fundamental counting principle is not going to work. And then last thing on this slide, wrapping this up, a permutation is a situation where order matters, and combination is a situation where order doesn't matter. So, some comparing and contrasting. How many ways can a president, back it up with the prompt here. There are 10 people in a class. How many ways can a president, vice president, and secretary be chosen in this class? Well, being chosen president is different than being chosen vice president, which is different than being chosen secretary. So order matters. This is a permutation. We could solve it using regular fundamental counting principle, or we can solve it by using the formula. And we'll use this problem here as an example of knowing where this stuff is on your calculator. Okay, the NPR and NCR have functions on the calculator. Let me zoom back out here. Oh, wrong way. Get this like that. Zoom in a little bit. That looks like it's pretty good. If you go to Math and then over to the Probability menu, there's NPR and NCR. So for NPR, we would choose number 2, and you can put in a number as basically just as they appear in written form. There's the 10, there's the 3, hit enter. All right, back to this for a moment. Same class of 10 people, how many ways can a group of 3 students be chosen to represent this class? So from 10, we're picking 3 of them, and it's a combination instead of a permutation because order doesn't matter. You're just chosen to be in this group or not. There's no president, vice president, or secretary. There's no captain, co-captain, water boy of the team or anything like this here. You're either in a group or you're not. It doesn't matter whether you're picked first, second, or third, or a claw breaks through from the ceiling and grabs 3 people all at once. Interesting thing. All right, so back to this. You could use that formula in a raw form from the last slide, or chances are you're going to do this right on your calculator. Math, PRB, choose the NCR function, type in the 10, 3, enter, and there's your 120. All right, one more example that distinguishes a permutation from a combination. A singing class has 8 students. How many ways can the teacher choose 3 students to sing a trio, 1 student to sing, another to hold the music, and a third to play the piano? So here, you're just in the trio or you're not. There's no distinguishing between who's chosen first, who's chosen second, who's chosen third. Combination. Here, we're picking 3 people with 3 individual responsibilities. 1 person singing, 1 person's playing the piano, another one's holding the music. If I had to guess, this would be the least talented person in that particular group, but that's a different story. So, back to the problem. If it's a permutation, chances are you're going to be able to solve it using regular fundamental counting principle, or you can use the formula in its raw form, or you can use the NPR function on your calculator. Again, this is considered to be background knowledge, stuff you're already supposed to know coming into AP Stat. So we're not spending a whole ton of time on this. This kind of is what it is. Know the calculator keystrokes, know where to identify it. This is going to be the small part of something larger in a moment. All right, now getting into actual what AP considers AP level material here. A term called Bernoulli trials. The basis for probability models we will examine in section 6.3 is the Bernoulli trial. We have a Bernoulli trial if there are 2 possible outcomes, success, failure. The probability of success for whatever it is we're doing, which we're going to call P, is constant, and the trials are independent. So knowledge of what happens in one trial does not give us any information about the probability of the next trial, etc., etc. Okay, the actual term Bernoulli trial is not used in our textbook. It is commonly used in many other statistics texts, and one you should be familiar with. The MathXL book that we use, or the book that our MathXL program aligns with, uses the term Bernoulli trial. Very, very common on websites. It's one you should be familiar with. All right, now that finally leads into the binomial model. A binomial model tells us the probability for a random variable that counts the number of successes in a fixed number of Bernoulli trials. All right, we've reached the point of the course where a very common question is going to be identifying if conditions are met in order to be able to do a certain type of, in this case, probability problem. Soon it's going to be inference. So, one of the common AP questions has to do with, are conditions met in order to be considered a binomial setting, or a problem where it's appropriate to solve it with binomial probability. A binomial setting arises when we perform several independent trials of the same chance process, Bernoulli trials, and record the number of times that a particular outcome occurs. The four conditions for a binomial setting are, well, three of them are just slight rewordings of what was here, and then there's the fourth one that will distinguish this from the other type of probability we're going to do that's included in 6.3, known as geometric probability. So we have a nice acronym. We have BINS, B-I-N-S. B stands for binary. The possible outcomes of each trial can be classified as a success or a failure. I stands for independent. Trials must be independent. That is, knowing the result of one trial must not tell us anything about the result of another trial. N, the number of trials N of the chance process must be fixed in advance. And then S, there is the same probability of success P on each trial. As with anything we do in this class, if you see the question and it's asking you to verify a setting as being binomial or not, you need to make sure that each one of those things are put back in the context of whatever the problem-solving situation is. Stating the generic, like it is here, is not going to get you full credit, perhaps not any credit on that particular question. All right, so now on to the formula. The binomial coefficient counts the number of different ways in which k successes can be arranged among the n trials. The binomial probability, x is equal to k, is the count multiplied by the probability of any one specific arrangement of the k successes. Okay, this by itself probably doesn't mean a whole lot. We need to kind of flesh it out with the rest of the formula. So if x is the binomial distribution with n trials and probability p of success in each trial, the possible values of x are 0, 1, 2, all the way up to however many are appropriate to the problem. K is any one of those values. So the binomial coefficient that they're talking about here, that's that NCR, or the n over k, and then in this case the formula your book uses a k instead of an r. Your calculator uses r. R is pretty common. It's not necessarily the letter that's there as to what it's doing in the formula that's more important. So P is your probability of success. K is how many successes you're interested in. 1 minus P is your probability of failure. And if you have n total trials with k successes, then you have n minus k failures. All right, so on to some examples that use this. Suppose you are taking a 10-question multiple choice test. Each question has 4 choices. If you randomly guess on each question, what is the probability you get exactly 3 correct. So that's the number we're interested in terms of the number of successes. That's our k value. We want to know the probability of getting exactly 3 correct. N is our number of trials. Each time we guess, that's a trial, we're guessing 10 times because there are 10 questions. Your probability of success is 1/4. That's because each question has 4 choices. So you have a 1 out of 4 choice of guessing correct, which means your probability of failure is 3/4. So plugging that information into the formula, NCK That's the same combination that we started off the class with. So, number of trials, interested in 3 successes. There's a 1 out of 4 chance of success. We want 3 of them. A 3 out of 4 chance of success. We want 7 of them. So there's about a 25% chance of getting exactly 3 questions correct. All right, suppose you are taking a 10-question multiple choice test. Each question has 4 choices. If you randomly guess at each question. So this is the same setting that we had on the previous slide. What is the probability to get at least 8 questions correct? Okay, at least 8 means it could be 8, it could be 9, or it could be 10. So what we have to do here is get the sum of 3 individual probabilities. So what we need to do is use that formula 3 times. So, 10 choose 8. The number of trials, this is how many successes we're interested in for the first part of what we're writing out here. 1 out of 4 chance of getting it correct. That's going to happen 8 times. That number always has to match this one. 3 out of 4 chance of getting it wrong. Well, if there are 10 trials, 8 successes, there must be 2 failures. So with 3 out of 4 chance, it's going to happen twice. So we're getting 8 correct, 1 out of 4 chance of that happening. We're getting 2 incorrect, 3 out of 4 chance of that happening. This calculates, well, what are the different combinations of which ones are correct and which ones are not. So now we just need to adjust as we go along. So this is for 8 successes, this is for 9 successes, this is for 10 successes. So the probability of success and failure isn't changing. Here, that 9 matches that 9, that 10 matches that 10. If that's 9, this has to be 1. If that's 10, that has to be 0. So, very small probability here, about 0.04% chance that you get at least 8 questions correct, which translates to about a 1 out of 2,500. All right. As you're aware of by now, many of the word problems that we do in this class tend to have a medical setting of some kind. So here's a problem that addresses that idea. Each child of a particular pair of parents has probability of 0.25 of having blood type O. Suppose the parents have 5 children. Part A, find a probability that exactly 3 of the children have type O blood. All right, so our N is 5. Each child is a trial. Our probability of success is 0.25, which makes our probability of failure 0.75. And we're interested in exactly 3 successes. So this one here uses that parentheses notation. That 5 over 3 inside of parentheses means the same thing as 5C3. 0.25% chance, a 0.25 chance of being successful in this case. What is successful? Having type O blood, that's happening 3 times. 0.75 happening twice. So a little less than a 9% chance that you'll have exactly 3 children with type O blood. All right, part B, should the parents be surprised if more than 3 of their children have type O blood? All right, so first of all, remember something we've talked about a couple different times. The basic default is 5%. For that being an unusual event, are you surprised type of thing. So if the probability that we calculate is less than 5%, that would fall under the category of, yeah, we should be surprised. If it's more than 5%, typically you're not going to say or classify it as being a surprise or an unusual event. Okay, back to the probability at hand. If more than 3, that means it could be 4, it could be 5. Binomial probability is a discrete probability distribution, which means endpoints matter, in contrast to when we did continuous probability distribution where endpoints didn't matter. Greater than 3 is different than greater than or equal to 3 when you're doing a discrete probability distribution. So that means it's a probability of 4 plus the probability of 5. So similar to the way we set it up, plug in all the numbers for for the 4, plug in all the numbers for the 5. So out of 5 trials, we're interested in 4 successes. A success has a probability of 0.25, the happening of the 4 times. If there are 5 trials, 4 successes, there's 1 failure, probability of that is 0.75. So we end up getting about a 1.5% chance. Since there's only a 1.5% chance that more than 3 children out of 5 would have type O blood, the parents should be surprised. All right, now something that's happening here is this problem involves sampling without replacement, something that will be addressed in more detail soon. Okay, once you're sampling without replacement, that independence thing in the bins becomes a potential issue that we have to discuss, and we're going to get to that. I don't know if it's the next slide, but soon. All right, some more examples. A standard fair 6-sided die is rolled 25 times. Each side is numbered 1 through 6. Find the following probabilities. Rolling a 2 exactly 5 times. So, n is 25. Each time we roll the dice, it's a trial. We're interested in 5 particular successes. A success being rolling a 2. 1 out of 6 chance of rolling a 2, it's happening 5 times. 5 out of 6 chance of getting something other than a 2, that's happening 20 times, at a 1.8% chance of that occurring. Okay, rolling an even number exactly 12 times. So, out of the 25 trials, we're interested in 12 successes. An even number, half the numbers are even, half are odd. So, half happening 12 times, this represents the evens. Probability of half happening 13 times, that represents the odds. Okay, rolling a multiple of 3 exactly 8 times. So of the 25 trials, we're interested in 8 successes. Multiple of 3 would be 3 and a 6. 2 out of 6 is a 1 out of 3 probability happening 8 times. 2 out of 3 probability happening 17 times. Okay, next slide. This is the one that addresses the sampling without replacement. All right, so some background of why this is going to become very important to us. The binomial distributions are important in statistics when we wish to make inferences about the proportion P of successes in a population. Okay, once we finish these chapters 5 and 6 with the probability, the rest of the course, well, most of the rest of the course is going to have to do with inference. Taking your data at hand that's based on a sample and making some kind of conclusions about the population. Okay, the binomial distribution is leading into things that's going to be a big deal with that. Okay, almost all real-world sampling, such as taking a simple random sample from a population of interest, is done without replacement. However, sampling without replacement leads to a violation of the independence condition. So thinking about like a deck of cards, which we've done many, many times, if we're sampling without replacement from a deck of cards, after we take the first card, the result of that first card affects the probability of what the second card is going to be. And therefore, we don't have independence. But what happens when you have very, very large populations, the effect that that has becomes negligible. It's many decimal places further than we need to be rounding our final answer to. So, here's how we're going to handle it. When the population is much larger than the sample, a count of successes in a simple random sample of size n has approximately the binomial distribution with n equal to the sample size and p equal to the proportion of successes in the population. And here's what we're going to do to quantify that large thing. When taking a simple random sample of size n from a population of size big N, we can use a binomial distribution to model the count of successes in the sample as long as n refers to our sample size, less than 1/10 of the population size. Or a more common way you see that written is your sample can't be more than 10% of the population. Now, we're going to be using that as a condition here for the binomial. It's also going to be a condition for lots of stuff that we do with the inference. That's going to be a common thing that you're going to have to address, that when you're sampling without replacement, we have to make sure we're not sampling more than 10% of the population. All right. The rest of this slide is just practice problems here. And I see this video is already getting on the longer side. I'm just going to write down the answers to these two guys here. If you want to pause the video and try these on your own, you can, and then check your answers. For A, 4 decimal places, which is a common safe rounding for probability problems at this stage of the game, you should get 0.2461, 0.2206. Okay, this one I want to do with you guys because it emphasizes a relatively important thing that we haven't addressed in detail so far. I don't know if I've talked about this yet before in the class, but when I taught a different statistics class a long time ago, when both of my kids were very young, I used to spend a decent amount of time watching SpongeBob with them. And when I made up worksheets and quizzes and tests, very often I would put a SpongeBob theme to them just to make them somewhat more interesting. And some of those questions have survived over the years, and this happens to be one of them. When Patrick and SpongeBob play their favorite video game, Patrick wins 60% of the time and SpongeBob wins 40% of the time. For part A, what is the probability that Patrick will win exactly 4 of the next 7 times they play? So the number of trials here is 7, and we're interested in 4 successes. Now you have to pay attention to what's a success. For part A, a success is Patrick winning. Well, Patrick wins 60% of the time, and we were interested in that happening 4 times. That means a failure would be 0.4. 7 trials, 4 successes, it means this must be a 3. Okay, for part B, what is the probability that SpongeBob will win exactly 5 of the next 8 times they play? So for this one here, it's 8 trials. We're interested in 5 successes. And SpongeBob winning is now the success. SpongeBob winning is 0.4. 5 times. This is going to be 0.6 3 times. So the reason why I wanted to do this problem with you was to emphasize you need to pay attention with what's the success and what's the failure. In some situations, it's kind of obvious that it's going to be a whatever. In this case here, here's 2 questions where what's a success and what's a failure switches depending on the wording of the question. So that's a detail to make sure that you're paying attention to. All right. This one here, for the interest of time, again, I'll just write these answers down. You want to try these on your own, pause the video, and then check your work. For this one here, you should end up getting a final answer of 0.0895. This here is an extremely unlikely event. It's about 3.3 times 10 to the negative 10th power. So it's extremely unlikely that that particular set of events will occur. Okay, that is a wrap for today.